Thank you very much for the introduction and for having me, of course, here. So I did go also a similar path preparing slides, saying what is it really that I'm passionate about? And of course, I'm passionate about all of my work, especially work that I do at NVIDIA. There's lots of exciting things going on. But in part also, I'm really passionate about unsolved problems because they are so much more interesting than just talk about all the great things that we have. So there are a couple of slides towards the end also that illustrate a little bit better what we have today, what cool things you can do with it. Hopefully that will make you curious and make you look. But a good part of my presentation, especially at the beginning, is really motivating where I think quantum computing needs to focus its efforts on today, what's kind of happening in that direction. And I hope there's something new for you to take away from that in today's presentation. All right, so with that, let's get started. Now, NVIDIA, HPC, and quantum computing. There is a lot happening here in Europe around integrating quantum hardware into HPC centers, which was really nice to see. Not quite as much in US, lots of hardware manufacturers, lots of cool hardware there, but a little bit less HPC integration. Here, more interest there, which is nice. But I want to drill down a little bit more into that as we go. By and large, of course, we do expect that ultimately quantum hardware will be available as part of centers. For one, of course, it's just not something you have in your basement. Usually qubits are fragile, need to be cool, need their own nice space, so not something we have at home generally. And then we do also, of course, expect that on one hand, quantum computing is very useful for a lot of the applications and use cases that are dealt with there. Think AI, think, chemistry, all of these things. But conversely, also there's just a lot of classical compute that is required to actually have a functioning quantum processor. So we do also need other accelerators like GPUs, for example, to really make use of a quantum processor. So if you've been in one of the NVIDIA presentations lately, you probably have seen a diagram, something like this here on the right side. Now, I promised I would drill down a little bit further today into the actual more interesting pieces. It's still pretty high level, but there are a couple of things I really want to call out. So let's look at this. On one hand, of course, we've got some sort of front-end service, programming language, whatever. I'll skip that part a little bit. But then we've got the whole infrastructure connecting the actual quantum hardware with the rest of the system. And here's where the interesting pieces happen, right? Because I'm already going to start out here with this little box around the quantum hardware, basically, that says error correction layer. Yes, I'm going to be talking about how does this really need to look like to actually have a processor that also is error corrected, connect successfully with the rest of the system, other classical accelerators, and so on. So once you have that, you definitely do have some amount of classical compute close by. Maybe that's a lot of electronics, maybe lots of ASICs. We already have that today. There's a lot of electronics needed to interact with the quantum processor. But to a degree, it's also reasonable to expect that probably there's some software there in the mix, especially during early development. Today, a lot of that happens on FPGAs. Because they're programmable, we don't necessarily have full confidence yet on what exactly error correction code is going to be like, what the exact decoder is. So there's always a lot of value in not yet having dedicated hardware built, even if you know eventually this is all going to get burnt into hardware. Right. Then that whole system talks, of course, to the runtime. And the runtime, basically, that can have any code in it. That can have, the standard parallel code. It can interact with GPUs, CUDA kernels, all of that, right? And then there's this moment when it calls into the quantum kernel. At that time, it's going to have to do basically a JIT compilation to finish compiling the actual instructions for the quantum device and push that down at some point, literally into a fridge. So when you see this, first takeaway should be, I mean, clearly, yes, in the end, quantum applications aren't just about the quantum part. There's a lot more to them. There's a lot of getting data in, getting data out, and all of that. Now, we're at NVIDIA are really focused here on the system development and the exchange between processors, because this is also what brought me to NVIDIA. There's just so much experience actually having done that with GPUs, and GPUs are to a degree somewhat similar as quantum processors. They have some of the same strengths, of course some differences, but there's a lot that can be learned from that integration, and so we want to apply that to actually build a system. Now, we do want to be focused that we're not specialized to a hardware. That's another thing that I really, really like about it. Most bigger companies that have an investment in quantum computing have taken a bet on a particular qubit architecture, so to speak. But, I mean, it can be nice. It makes it a little bit easier, maybe, to think about the problem and solve it, because you can specialize for that hardware. But personally, I think trying to generalize is a good start, because it really forces you to think at the conceptual level. See what are the similarities, what are the right structure of this problem, this compilation stack to think about. And this is why I really like to test this version in my head against reality, so to speak, and really see, does it work with different kinds of qubit? Does it hold up? So I do think it's a strength and an asset, and that's exactly what we do here. All right, and of course, we do want to enable low latency scenarios. So, second piece to call out, I really want you to take away from this presentation today is this accelerator process. I already said, of course, we've got the things that actually happen on the quantum hardware. Some fields apply to it, quantum state changes, but there's real-time computations that go with that. And the important part is, when you do go to other talks about quantum computing, especially the ones that are a little bit more focused at the surface level, at the here's what you can do with the things that we built, they're going to tell you about hybrid system and integrating quantum hardware into HPC system. Now, in I think pretty much all cases where I've heard that, they're talking about host process and the quantum computing part. These two together. No real-time computations in between. No real-time computations for application code. Of course, there's some classical processing happening, again, to make the quantum processor work, but that is not available for use in your application. And that's the very, very big difference. There's hybrid and there's hybrid, all right? There's hybrid and there's tightly integrated. We're going for tightly integrated. That's the part that I'm personally passionate about and I've been pushing for, trying to work towards, and it's very hard to get working, but a lot of fun. So that's the second big takeaway for you. Do ask what hybrid means, you know, and we want something more than just basically a one-shot communication. If you just have host process and the quantum computation, what that means is that when I call from my classical application code into a quantum processor, I send code down at that time, that code runs, I get answers back up, and then all the quantum resources are deallocated, basically. Your state doesn't live past that. You can't come back later on and ask it now to do something on top of that. When I'm talking about real-time compute, what that means is that I get to talk back and forth. I get to get responses from the quantum device, compute an angle, depending on some measurement results, and then tell the quantum processor to continue its computation with new input now. And that's the part that's going to unlock a whole different set of applications if we can make that work. And there are some companies who do have support for that, by the way. This is not all hypothetical. This is reality. It's just not necessarily very carefully distinguished. It's kind of harder to promote, maybe. You know, HPC integration sounds great. This one requires explaining, but be careful about that. All right, summarizing what I said here, basically, important distinction is, you know, if we do have a separate process, basically, for each call into the accelerator, there's exactly just this one-time communication between the host and the accelerator process. And what we do want to have is really persistent, basically classical and quantum memory across the different processors. So now I said it's very important. Let me at least give a couple of examples on why it's important. It's always good to explain sort of where the take is coming from. So for one, clearly, we need that for control flow. And since error correction today is mostly treated like an application code, it's basically needed for error correction. You know, if you do want to do real-time error correction, you do run your error correction code like an application code. At the end, you measure some syndromes, you get data back, you do some processing of those, and that tells you what correction to apply. Now here too, a lot of error correction research today really just looks at having quantum memory. It doesn't actually run application code on top of the error correction layer. It's just having qubits sit there and measuring how long they can sit there and stay in the state that they're supposed to be in, right? If you do that, you can do it all offline, basically. You can just gather all your output from the error correction code that you gathered for a certain duration, and then take a month to process it. Doesn't matter how long it takes. Get the answer and check at the end, oh, was I able eventually to correct correctly? But as soon as you have application code that runs on top of your error correction layer, then there are certain things in the application that will force you to apply the correction, because you basically can't permute the next instruction with the correction that you need to apply. So that means now you need to be fast with processing on one end, and also you need the quantum state to remain coherent while you prepare the input that tells it what correction to apply, right? So clearly we do need control flow eventually for error correction. And here too, the first demonstration of that has already happened. Quantinum, for example, very nice hardware, very nice company, lots of that is exactly building on what I'm talking about. We're working with them before, I've been working with them before getting to NVIDIA. So, you know, again, this is something that exists. It's not all just on paper. Now, the other reason though why real-time compute is important is that basically, you know, there are workarounds today. People are creative. Of course, you get things to run, and as long as your application has 10 qubits that require 10 angles, that's kind of fine, and 5 iterations, all right. That's a very tiny lookup table, really, to say, okay, let me just evaluate anything classical in my code ahead of time, store it somewhere, and then I don't need to do any real-time computation. But as we scale this up, keep in mind, real quantum applications claim will have arbitrary control flow structures, much like classical code has. Just look at how other accelerators are used. GPUs are used, how FPGAs are used, and so on. You see how complex these applications eventually need to become. And then it's really infeasible to really have this gigantic table to look up all the values that you're ever going to need. I should also say, once we're talking about error-corrected device, you do need to synthesize rotations. So today you just apply a rotation gate, less directly with a pulse usually, kind of close enough, or at least not noisier than anything else on the device. But once you have error correction, what you need to do is have an actual finite set of instructions that you translate everything else into. So when you see something like rotation by pi over 4, you got to have to approximate this with some h and t's and so on, right? And here too, if your angle depends on measurement results, it is somehow need to retrieve that sequence in real time. You can't even compute the table for that, so you need a better approach. Then last but not least, if you actually run on quantum hardware today, you will find the code size is one of the limiting factors. You very quickly can end up trying to submit a code that doesn't use too many qubits, isn't even too deep or too long, but just code blows up. Because inlining everything, unrolling everything, yeah, it gets a little bit large, right? And not necessarily efficient. So if we can preserve the right kind of abstractions and do some amount of real-time compute that enables that, everything just overall will get much more efficient. All right, So bottom line is, we do want real-time compute because workarounds are ultimately going to be too expensive to do and not realistic. And if we can get there, there's a whole universe of new applications. We've barely scratched the surface in terms of what quantum applications can really be, because everybody has been focused on, what if I just have a giant unitary? There's a lot more than that. There's heuristics. Look at all the heuristics and what you could do with it. Now, how do we make this happen? So on one hand, even for hardware that doesn't have support for real-time computations today, clearly we already leverage a lot of infrastructure. So for example, a lot of the hardware providers do have GPUs for one reason or another. One being that, if you look at error correction, of course, and you want to do something fancier maybe than just a tiny min-way perfect matching, maybe you go with AI and machine learning, kind of cater to the noise model to get a better decoding, then, we're exactly in the world where just GPUs are really fast at doing that kind of work, so it pays off to have it. Similar things also hold for optimal control, where just leading methods are generally GPU accelerated. And then also calibration, very important ultimately. There's been a lot of work to cut down the time to actually basically boot up your system and get it into a functional state. And all that is very compute intensive. So it's not like the hardware isn't there. The hardware very much is there. And in fact, we've seen kind of Grace Hopper devices being very widely used. Oh, okay. I think I'm good. Thanks. So, there's good processors there that have GPU, CPU very tightly connected. They could, in principle, be used to put the runtime on it, have all the chip compilation happen there, and maybe even directly connect effectively to a quantum processor so that GPU and QPU can talk directly, for example, for the purpose of error correction. But it's not so easy to use that. This connection is kind of tricky. Again, whole fridges around it, so, there's always custom work needed. And the custom work, unfortunately, is for every different qubit architecture, there's a slightly different kind of work to do. So the only thing we can do here is to actually take it step by step and be part of that development and help people with it, right? So I have no intent to just sit there and wait for somebody to tell me that I can hook up the QPU now like I do the GPU. We actually do want to help figuring this out. And so at the very high level, let's talk about that. So we need a vision for the future. Vision is good to have because somebody today is building what we're all going to be using in 5 years. I'm making no claims. I'll let you be your own judge on whether we are that entity or not. But somebody is. And if everybody just thinks about the needs of today, then 5 years from now, we're still going to be stuck with what we had today, basically. So it is important to see where this whole thing is going. Now, it's nice visualization there, of building a car. Maybe also not quite optimal in that way, because we also need to be a little bit practical about this whole thing, right? So a better sort of graphic that you see, if you've looked at sort of development processes and so on, is that rather than starting with a wheel and then 10 years, we basically come back and say, yay, finally, our quantum computer is done. We do have a sort of something that works kind of, like a skateboard today, and then that evolves. It doesn't stay exactly the same for the entire duration, but we do try to roughly incrementally get where we want to be while keeping it somewhat functional in the process. Now, the risk with that is overfitting, basically, right? At different stages in the process, it makes honestly sense to build different software. And I think this is exactly what we're seeing today. For a very, very long time, all the quantum computers could do is unitary, measure all qubits. That's it. For that, honestly, a custom abstraction and a custom compiler basically makes perfect sense because it's so ridiculously simple. It's mathematical. Probably just formal verification tools are most suited to do that kind of work. But once we progress beyond that, where we have control flow, mid-circuits measurements, and so on. Now we're starting to talk about really building a compiler, much like the classical compilers. And I'd argue now we're past the crossover point where any sort of Python library that is a custom compiler makes sense. We really do need to build state-of-the-art compiler tools, which is why quantum computing as a community, I think, has moved to LLVM, just like we have. Very happy about that. 2 years ago, I was the one very much pushing for that and launching that effort, and now I think we are there. And a lot of the major frameworks have either done that or are in the process of doing that, so that's great, right? So we do want to adjust for what we need today and kind of meet the need, but also if we're perfectly meeting it today, then chances are that we're not actually heading exactly where we want to be. And last but not least, a lot of this just is still requiring more research, requiring ideas, requiring smart people to solve the problem. And I have no illusion that I have all the answers. I do not. NVIDIA doesn't have all the answers. Nobody has all the answers, which is exactly why we need to be comfortable with the notion different people will bring different expertise, and what we do need is some formalization, standardization. It's not a bad word. 2 years ago, this was a bad word. In quantum computing, now again, I think we're starting to be better about that, so that in the end, we can each build the pieces we have the expertise for and everything fit together. So I said, it was a couple of years ago, that I'd been advocating for that. This was what the QIR Alliance was launched to do, literally, on one hand, to get everybody to actually use state-of-the-art compiler tools, and to make a first step at really a commitment to develop the interfaces basically together so that everybody can build bits and pieces and still guarantee that it fits together. I'll very quickly say the main goals there at that point that still hold today, of course, are allow for incremental progress. It's not hard to define what the future should look like. It's not hard to see what the today looks like, but the gap from today to the future, that's the hard part, right? Because I can't just go to a quantum hardware provider and ask, yeah, I now need vectors of floating point numbers. When can I have them? It's not going to happen. It's a lot of conversation. Integer support has been great. I've had so many conversations about whether 18 bits are okay to have, or does it really need to be 32, and things like that. We have left shift, but not right shift sometimes, and things like that. So it does need to be incremental, opt in, opt out. So at the same time, of course, a lot of software efforts, especially if they need to support a range of hardware providers, software providers, what they ultimately end up going for is the least common denominator, right? Because the thing that works across platforms is the thing that every platform supports. It makes life a lot easier, but it's also holding us back from actually taking advantage from real cutting-edge features that some hardware providers can make work. So we're not doing that. Makes it a lot harder to provide a good user experience. So if you ever run into a place where compilation just rejects the code and is not very nice about their message, bear with me. At least I'm trying to get you the features that are actually, unique for each platform. Then we do, of course, want to make sure that we can integrate this with other existing tools, and classical HPC and so on. And we want to stand on the shoulders of giants, right? There's decades of compiler research. Quantum folks are not going to reinvent it. We're just going to extend it, so to speak. All right, so back to CUDA-Q. Now, at the front, let me quickly walk you through a little bit the representations here. So we do support both C++ and Python as a front-end language, so much like CUDA, that is basically expressed in C++, CUDA-Q also just supports effectively a subset of C++ and of Python. We are not a language extension, so intentionally we didn't make up our own custom syntax. We just basically say, yeah, annotate your kernel and mark it as a quantum kernel, and then everything that's in there is going to be extracted and piped through our own custom compilation pipeline. In principle, this could be all of C++. Realistically, we need to handle every single construct in a custom manner. So they're more restrictive rules, so to speak. You can't call arbitrary libraries from within a quantum kernel, since we have no way of getting that library down into a fridge and run there. All right. So I'll omit a larger discussion on exactly how do we do any sort of design time feedback to make your life as a developer easier. That's a whole other topic I can give a separate presentation about. If somebody has a workshop on that, for today, I'll skip it. Because we do translate basically then the language-specific AST. So we use the language tooling to get an AST. It's not something we custom write, Clang or Python interpreter. But we do then translate that into our own internal dialects. These are built on top of MLIR. MLIR is kind of giving us a nice tool set to just define the abstractions that we care about. It's kind of a level higher, so to speak, than QIR. We do pretty much all of our ahead-of-time compilation and also just-in-time compilation to an extent still on MLIR. By the time that's done, by the time we fully compile a kernel, it's basically at the LLVM level then at that point. And specifically, the classical code is compiled to LLVM-IR, the GPU code to NVIDIA-IR, and the quantum code to QIR, quantum intermediate representation. Now, QIR and NVIDIA-IR have the same approach. They're basically saying, well, it's LLVM with a more restrictive subset and special rules. Right? Because again, LLVM is just huge. And so you do agree in the community on what subset of that to use and how to represent specific constructs that are needed for your specific processors, right? So we have a very, very similar approach here. And then below that, we see that basically, all right, I put assembly as the classical sort of equivalent of PTX there, because it didn't feel quite accurate to call it machine code, even though Clang usually directly goes to machine code. The IR for GPUs is ultimately first compiled to PTX, which here, interestingly enough, is still GPU architecture independent. Then that gets compiled to machine code and runs on the GPU. For QIR here now, there's the interesting part, because Quantum hasn't really talked about that format, about that equivalent of PTX. And that's the part, I think that's the next evolution that ultimately needs to happen. Because what this is effectively an instruction stream. So QIR, if you've ever looked at LLVM or MLIR, you should be very familiar. It's very imperative, you know, still have sort of one expression per line or statement per line, so to speak, but very much sequential, you know, do a plus between these numbers, do a plus between these numbers, and so on. So if you use that for quantum, you still see H on qubit 1, H on qubit 2, and so on. It's not very vectorized, and it's certainly not actually having scheduling and timing information in the IR at that point. It's not scheduled, it's not resource bound, that IR. And so what I called here freely quantum very long instruction word format that is not existing today, to be very clear, but needs to come to life at some point, is a representation that basically says what does each logical qubit do for the next cycle. And then you push these cycles down into a buffer where a quantum processor can retrieve them and execute them, right? But this would then be a fully scheduled representation. So any sort of coordination still remains basically in the runtime. When the runtime generates these streams with data that it pushes down, basically, it makes sure that by the time it gets responses back up, which are buffers of measurements, really, it knows where to put them, so to speak. But it really, at this point, has made all the decisions regarding what part of the chip are used for which computations, so to speak. All right? Now, the reason that this is still at the logical level is, again, just bandwidth. Because if this is all in a fridge, pushing down physical pulses, it's not going to happen as we scale up. It's my claim. All right? So, because somebody will always ask, where's my pulse layer? Here, below that. All right? Under the error correction. So once it gets down into the fridge at some point there, you're probably going to have something like an ASIC ultimately that takes care of that. All right, let me quickly break here. Any questions so far? All right, that's a lot. All right, let's go order around.
Yes, thank you for the talk so far. You said that for your Python interface, you analyze the abstract syntax tree and then basically bind the instructions to a more low-level interface. Is it also possible to call this low-level interface from a user perspective, or basically do you shield your users and the only way to access it is through this AST analysis?
Yeah, I mean, MLIR has a nice existing infrastructure basically for generating Python bindings for its dialects. So what we convert to are the dialects, right? And of course, you can basically in memory build, you know, the IR directly, so to speak. That's not usually very user friendly, but you can do that if you want. So from that perspective, it is exposed via the Python bindings that MLIR gives you, and you could directly interface with that. Beyond that, we haven't simplified that in any way or made it more convenient at this time. We do have only few compiler APIs exposed. We're adding a couple of more. If you do want to do something like that, file an issue on GitHub, and we roughly know. The issue that we don't expose more is more stability, right? Our own internals are still evolving, and you know, we're not entirely ready to expose everything for stability.
All right, thank you.
In the picture, it seems like 100% of the decision about what goes on the quantum computer and what goes on the classical computer is made by the compiler. Is there anything left for the programmer in that decision, or is it really all going to be the compiler from back-end agnostic downwards?
We do rely on programmer annotations for what fundamentally are quantum kernels, right? So that we see very clearly where's this interface where we launch a new process basically on the quantum computer. Now the real-time compute, of course, just because you write your classical addition in there doesn't mean it happens in there. We do very aggressive constant folding and things like that. Our CHIT compilation takes the call arguments into account, for example. So it's a combination, I think, of both.
I have two questions. So Oak Ridge obviously is another company that is very invested in the sort of embedded hybrid systems for acceleration. And one of the things that they've been commonly bringing up in their papers is the fact that HPC inherently deals with very large amount of data. And one, we don't have quantum machines that are able to sort of even represent that data. And two, even if one day we get there, the initialization process for that large scale of data will be the bottleneck. And they've been sort of speculating of like this sort of multi-processor distributed systems for HPC acceleration. I'm curious if there's something going on in NVIDIA regarding that problem. And the second question is, I'm also curious about to what level you're actually backend agnostic, because there's very significant differences between digital and analog quantum computers, something like D-Wave machines. They're programmed very differently, and if you could speak to that a little bit.
Well, all right, let me start with the second question first, and coming back to the question on data input-output. So yes, I've not introduced any sort of distinction between kind of annealing devices and gate-based devices and so on. We do, of course, at the application level, so to speak, you can all bundle that up nicely in one holistic framework, so to speak. It's just libraries under the hood, and then you have very high-level solvers, so to speak. It says, time evolve, please, this Hamiltonian, and that's it. And we do try to we are in the process, in fact, on defining how these interfaces look like, to just define Hamiltonians, have some sort of evolution and so on, that kind of fit in. We usually combine that with gate-based, probably less so, and within the compiler, of course, how this gets translated is very differently. So the answer is, of course, we do need to make custom investments ultimately for each backend. Also in terms of, whether we compile for superconducting or compile for ions, compilation is slightly different, right? So it's not that automatically, if you come up with a new qubit architecture tomorrow, it will just work. But from a user perspective, that's, we invest basically making that happen.
follow-up question, sorry. On the PTX is basically shielding, not only users but also developers from actually being able to access the GPUs. But does this also mean then on the quantum side that CUDA and in this case NVIDIA will control internally the development of drivers which are very complex and evolving and very different to quantum processing units?
So you'll see CUDA-Q maybe having some differences in terms of how it's rolled out and positioned already compared to what CUDA was at the time. One difference is that explicitly we're not manufacturing quantum hardware, right? By the time CUDA came out, it was very different. NVIDIA very much was actually manufacturing the hardware for it. CUDA-Q is fully open source also, so not the proprietary software that you're used to from CUDA. And as you've seen at the QIR Alliance, now our focus is to work with people to help define that. But our goal is to be a facilitator, really, that also has the liberty to look at all the different architectures and try to identify what makes sense without any stake towards any particular kind of architecture. But we're definitely not dictating anything here. It's also not per se intended to shield, though I do think there's a lot of value in a separation of concerns in the stack, right? And encapsulation, so that's going to happen. Yeah. All right. If you don't mind, I'll take the Oak Ridge question offline and we'll proceed a little bit because I do have a time heads up here. Okay, so now I'll skip more details on MLIR, LLVM. I think the audience here, you're all very familiar. It's a great framework. It's open source, lots of research happening there. That's all the reason why we use it. And of course, there's a lot happening during compilation. Here too, for this talk, I don't want to talk about the detailed pipelines, and please don't take a screenshot and like, here's exactly how it's going to be compiled. No, and this is not even how we compile. There's a lot of loops in there, generally. It's not quite that simple. But main outline for compilation is that we do have a split compilation model. As I said, basically we do have at the source level potentially everything in one file, quantum kernel, surrounding code, calling out to other libraries and GPUs. But then we actually grab the relevant bits and pieces and feed it into our own pipeline and have a patch up basically at the end. This again is very similar ultimately to how also CUDA compiler tool chain works. And it allows us to make our own decisions really for when to compile what. So what we do in check as part of this process is on one hand, of course, the necessary infrastructure for data exchange between different processors. That's the idea, to automatically handle that to a good degree, but also just the infrastructure to actually have JIT compilation invoked when it's needed and so on, right? And what this gives us is that at the source level, our source code still has MPI. I can use in there OpenMP, all the standard tools used for parallelization, and that's all handled via the runtime that we have. So back to our original high-level slide, CUDA-Q as a tool chain makes it available in popular tools, makes popular tools and libraries available, C++ and Python currently. If somebody wants Rust, I really want people to upvote having Rust in there. Right now I don't have enough demand for that. We do support a diverse range of QPU architectures. Often hardware providers actually contribute the basic integration. Right now that's a very not tightly coupled integration, but we do have ongoing projects. For example, with Quantum Machine is the one that was announced. We do have some other ongoing projects for tight integration, and hopefully next time around at the workshop, I'll be able to tell more about those. We do want to make sure that we can seamlessly transition to a large-scale system, and we're compatible with all the modern tools. And we also want to make sure that we can actually make this advanced functionality available. So our kernels are not a builder model where you just attach gates to your quantum kernel. There are actually kernels with classical compute in there. If we can run it on the quantum hardware, we'll run it on the quantum hardware. If we can't, we'll compile it away as much as possible. If it's entirely impossible to compile it away, then you'll basically get a compilation error when you try to target a backend that doesn't support it. Hopefully that should give a cohesive enough user experience and provide the necessary flexibility also to do further research and development with the stack. All right, so check out GitHub. This is mostly all open source. Couple of nice things that we have in there and some graphs in terms of performance benchmarks. Our language model does have quantum-specific things in there, like sampling, observe, just common patterns that people use in quantum computing. And under the hood, we specifically invest into optimizing those. A recent plot between 0.6 to 0.8. 6 was January, 0.8 is this summer, is that we have optimized a lot of under-the-hood handling, coordination, processing. That will give us a good factor of speed up here. Then we do also have quantum-specific data structures like spin operators, means to define a Hamiltonian. And to a degree, we do use OpenMP, for example, under the hood to parallelize when it's reasonable to do that. Right, so processing times are very much cut short. Only the quantum time remains. Then generally, a lot of what we have is multi-threaded, amenable to parallelization. If you have multiple kernels, of course, you can use MPI to distribute them across a range of processors. You can also do that across other arguments. So if you have this Hamiltonian with a lot of terms, for example, you can parallelize across terms. And then as you scale up and use more virtual QPUs, so to speak, you can really see how much this would accelerate your application. Since most systems don't actually have more than one QPU right now, you do have simulators to mock up the QPUs if you don't have 5 of them concurrently available to you. Our simulators are very fast. There's different slide set on that. We do have state vector-based simulators, tensor network-based simulators. We're working on support for really fast trajectory-based noisy simulation coming out sometime towards the end of the year. So for those that work on that, that should be interesting. And last but not least, we do actually started to expose a little bit of APIs to configure a platform definition that says, oh, I've got a platform with 5 QPUs and 3 GPUs. How would it look like now to work with those, right? So this is kind of where we want to go, what kind of work we want to see ultimately with the platform. And if all of that sounded interesting to you, then you should definitely check out CUDA Quantum on GitHub, PyPy, NGC, which is Docker images. You can also use the images with any other container runtime. And for those of you that now are worried that these tools would be awesome if they just had GPUs, there's also NVIDIA Quantum Cloud for those who don't have GPUs. All right, thank you very much.
Thank you very much. So I suggest that we set up for the next talk. And in the meantime, we have one short question. Yes.
Okay, yeah, I have more interfacing questions. So the MLIR dialect you talked about, is it something that you made up, or is it an existing dialect? And follow-up question, if I submit an MLIR file, is there an easy way to compile it down to QIR using your infrastructure?
So if you have your own custom dialects, right, you need to define your own basically lowering to LLVM for that dialect. We do use some of the existing passes, a structure control flow, for example, function dialects to represent callables. We do also have our own dialect, Quake, for the quantum-specific things that basically defines qubits and things like that. So it's a combination of the two. Now, at the beginning, when we started QIR Alliance, it was kind of a topic like, where do we go? MLIR, LLVM, where's sort of the right layer? And reason for us to stick with LLVM is that it's just for standardization, right? MLIR has the strength to be customizable. But that also means it's usually custom. So we don't try to standardize basically our MLIR dialect with anybody else. We have ours evolve even, between a year from now, our dialects are going to look slightly differently because we adjust to basically new needs. Hopefully all of that should be additive. So we should probably still have what we have today in the dialects, but maybe some additional abstractions. But if you do want a stable, basically, format, then yeah, this QIR is what the standardization is on, right?
Okay, thank you.
So thank you very much, Bettina.